Yeah, whatever. Okay, Cheryl, you're
Should we chase them in from out in the hall? Well, but I want everyone to hear me, so I don't have to repeat myself.
Okay, come in, sit down, pay attention.
We got the Germans up here now. So I know earlier Scott McIntosh requested that you guys send me PDFs of your talks if you're willing to have me posted on the website. I'd like to make the same request of the people with posters. If you'd like to send me a PDF of your poster, I will gladly link it to the agenda on the website. So just email that to me, or you can email it to me, condense it if you have to. Thank you.
Okay, and we'll start the next session with Shravan, who's going to tell us about solar dynamics using normal mode coupling.
Thank you for inviting me to this meeting. It's a privilege to speak on this occasion. I have a nice picture of Mike. I felt very close. I mean, Mike and I have known each other for now a decade, and I was quite close to him. We would meet, not so much, I suppose, academically, but is really a fun person to hang out with, and I would really talk to him quite a bit. This was a conference at Lorentz Mike and I organized in Bombay in 2015. What you can't see is Mike is actually wearing slippers there. He was looking super relaxed, chilled out, and as you can see, it's very sunny, and we had a really lovely time. So we miss him. I miss him quite a bit as well. Okay, so let me begin. I also want to say one other thing. This conference is really nice. I'm really grateful to the organizers for putting this together. The last time that I can reasonably recall having, all of the helioseismology community, all these familiar faces was, I would say, more than a decade ago, maybe 2006 or around that time, when Mike Thompson organized something in Sheffield. So it's really nice, and it brings back all these wonderful memories of when I was a graduate student giving talks and so on. So thank you for organizing this and putting this together. So I have some slightly dramatic things that I want to say. Not that dramatic, but but if you are in this topic, then it's going to be an unusual set of things that I'm going to say. So this conundrum was something that I suppose has always been known a little bit, but was sort of brought to the attention by a paper that with Tom Duvall and I wrote some years ago. And the basic problem is that numerical simulations dramatically overpredicted convective velocity amplitudes. Seismology said they were here, and the numerical simulations said they were here. There's been quite a bit of work. It launched a bit of a controversy at the time. There's been quite a bit of work since. And now I've begun to think that the whole enterprise is a house of cards for reasons that I will describe towards the end of the talk. But if you were to believe that this were the case, then there are fundamental challenges to our understanding of the sun, such as what props up differential rotation, what's happening with the dynamo, and so on. So everyone sort of pointed this out. I'll just say for 1 second that the fundamental issue here is that most numerical simulations and theory predict that the contours of differential rotation are aligned along with the rotation axis, whereas what we see in the sun is that they're sort of radially pointed. And this lifting of these contours is quite mysterious, and we don't understand. So Aaron was describing methods of local helioseismology, and so there's a certain class of methods that he described, but there's a different method called normal mode coupling. It's a very clever method. It's been in geophysics for several decades and was adopted by helioseismologists as early as 1989 by Martin Woodard. And the idea is you use global mode data, but you infer non-axisymmetric time-varying things. So you have the benefits of both. And the idea is mathematically very elegant, very beautiful. And so you have a simple model that's non-rotating, it's non-attenuated, it's just the standard Model S sort of situation. And then you get a bunch of eigenfunctions for the oscillations of this model. Those eigenfunctions are complete; they form a complete basis. And you have, of course, the sun, which breaks every one of these assumptions. It's rotating, it's convecting, it's attenuating, it's magnetic, all of these things. And so but the completeness of eigenfunctions of model S basically says that every eigenfunction of the sun can be expressed as a linear combination of the eigenfunctions of model S. So that very nice property is expressed in this equation, which says that the eigenfunctions of the sun are linear combinations of the eigenfunctions of the reference model with these coupling coefficients. So this is a standard quantum mechanics theory, so I'm not saying anything dramatically new here. And it's all within the realm of perturbation theory, the first Bohn approximation, single scattering, and so on. So very neat stuff. And the measurement of these alphas is the key of this method. Once you measure these alphas, you can build an inverse problem that then tells you what the difference between the reference model and the sun is. And measuring these alphas is not that hard, actually. So the one nice thing about this method is that it's very clean in terms of data analysis. So it turns out that these alphas, or these coupling coefficients, we call them the B coefficients. This is actually Martin's terminology, is a direct, there's a weight function here. It's theoretically derived, but it's directly connected to the cross correlation in wave number domain. So this is, phi is the signal that we measure, the time series of global modes at a given spherical harmonic degree and azimuthal order at a particular temporal frequency omega. So I'm just taking correlations of the wave field that I measure in frequency domain. And so you can write a very elegant theory that tells you what this function is. And this coefficient, this particular correlation, ensemble averaged, gives you the coupling between two modes. And it tells you, ostensibly in the sun, if the sun were a quiescent sphere that had nothing happening, then every mode is independently stochastically excited, and this should be zero. But it's non-zero because there's stuff that's happening. There's rotation. There's a lot of interesting things that's happening that's coupling these modes. So modes are sort of talking to each other. Or another way of saying it is an eigenfunction of the sun is a linear combination of the eigenfunctions of the the reference model. Okay, so that's the central tenet of the measurement aspect of this. It's really fairly straightforward compared to time distance or some of the other methods which require fairly elaborate and complex data massaging. There's very little that you do except compute these correlations and average them according to this equation. Now you have to go to the next step of interpreting these measurements. So unlike time distance helioseismology or these other methods which give you physically so time distance gives you maps of travel times, and so you can say, oh, I see something. It's something that you look at and you can make sense of. These are sequences of complex numbers, so they're much more abstracted. So you have to work a lot harder in this case to interpret what these numbers mean. And so the first step is you take, so we're trying to image convective flows here. You take the flow field and you use the Chandrasekhar-Kendall decomposition, which allows you to break or decompose any vector flow field into a poloidal and a toroidal component. And I want to point out that in the sun, you have these two terms which comprise the poloidal flow. This term comprises the toroidal flow. The toroidal flow does not carry thermal, or it does not participate in thermal transport. Thermal transport is exclusively accomplished by the first two terms here. The first term is a radially directed flow. The second term is a poloidal, like a supergranule, has horizontal flows that are going out. So these two terms are, yes, so that's the broad decomposition. You can do this at even more abstracted levels. So there are higher order functions called generalized spherical harmonics for dealing with magnetic stresses, Lorentz stresses, which are rank 2 tensors. So we have developed that theory. It's very it's algebraically, taxing, but very elegant. And so you continue with this algebra, and then eventually these measurements, those B coefficients that I said, were related to those coupling coefficients, are directly written in terms of this inverse problem. Okay, and so the goal of my talk is to tell you what I discover after I do this inverse problem. When I solve this inverse problem. So one last slide about normal mode coupling. It's a fantastic method. So you spend all your time on the analysis, mathematical analysis and interpretation. It's very beautiful, as I said, very elegant. Very little time on the data massaging, which I really enjoy, or which I don't enjoy. I mean, data massaging is a complicated thing, but the interpretation and the mathematics is much nicer. So I'd rather that particular trade-off. And that particular trade-off, I know what's happening in terms of attenuation. In terms of interpretation. With this, as I said, with this interpretation, you can model a number of issues like this systematic errors like line of sight and leakage and so on. There's the fact that you have realization noise. All of those can be fully accounted for. The most powerful thing that, I mean, it is possible to do this. Other helioseismic techniques can do this as well, but have yet not done this, is that it can take into account time-varying perturbation theory. The sun is temporally evolving. This is something we constantly overlook and ignore and wave our hands and say, well, we're looking at some average. But now we take this into account. We take into account the fact that the sun is temporally varying. So Martin Woodard, I give him much credit for having devised the theory for this. As I said, it can easily be extended to other helioseismic, not easily, but it can be extended to other helioseismic techniques too. Okay, so these have also been verified. The technique is not so new that I'm just saying this is a new method. We can measure Rossby modes. You heard from Aaron that Rossby modes have been measured independently through other means. We also see them through with normal mode coupling, so adding a point of verification. And we're now, and I won't describe this, but we can actually measure the Rossby mode eigenfunctions penetrating through the convection zone. So we're still trying to verify some of these results before we publish them, but that will not be the focus of this talk. There's, as I said, elegant inverse theory, and in this I want to specify that I've been relentlessly using Piper's and Thompson's very nice paper on SOLA, subtractive optimally localized averaging. It's a very nice technique, so just because we're talking about Mike Thompson, I thought I would point that out. Okay, so we sent this paper to review, and a reviewer pointed out that okay, the title, perhaps you could have come up with a better title. It's still in review, but one of the reviewers was very upset that we used the terms convection and toroidal flows in the same sentence. So the reviewer was not happy about this. But I want to point out, yes, as I said, convective transport, i.e. thermal transport, is accomplished exclusively by poloidal flows. But it is clearly a byproduct. The toroidal flows are a byproduct of this. So here is a simulation of Hideyuki Hotta. He shows, I'm showing here that the blue curve is poloidal power as a function of depth, and the dashed curve is toroidal flow power as a function of depth. As you can see, they're directly comparable. They're of broadly the same magnitude. In some places, toroidal flows exceed poloidal flows in their magnitude. So they are playing some important dynamical role. Exactly what it is not clear, but they're non-trivial. And so that is an important thing to keep in mind. It's very important to image toroidal flows. I am a little surprised that in the literature of numerical simulations, there is very little discussion of this type of what toroidal flows are doing, what poloidal flows are doing, and how these two interact. Please correct me if I'm wrong, but I haven't read too many papers that really describe this. And here's the HMI photosphere estimate by photospheric convection estimate by David Hathaway, and he sees as well that toroidal flows are basically comparable to poloidal flows, in fact exceeding poloidal flow magnitudes at low L's. So this is a surface constraint. So it is very clear that this is a very important measurement to make. And in fact, if you both these indicate that if you probably measure toroidal flows, it probably give you some indication of the magnitude of poloidal flows. Okay, so long story short, I get to cut to the chase and I tell you the answer. I spent a better part of 3 years now working on this. It's still not quite done. There's still some things that I'm tuning. But so there are many things you can do once you measure convection. So one is just the power spectrum. The second is the shape of convection. What forms of, where does it sit? What types of, what shapes do they take? And so here on the horizontal axis is S minus T. S is spherical harmonic degree. T is azimuthal order. So S minus T tells you the type of harmonic. So broadly, spherical harmonics are classified into sectoral harmonics, tesseral harmonics, zonal harmonics, and so on. These are different types of spherical harmonics. Sectoral harmonics are things that are sitting very close to the equator, typically L equal to M. So S minus T is basically 0, corresponds to things that are very close to the equator, sitting equatorially confined. Well, not exactly the equator, but within some range of the equator. Whereas when you go to very high S minus T, that means these are zonal. So for instance, this differential rotation or rotation itself is a T equal to 0, azimuthal order is 0, and it's only a function of the spherical harmonic degree. So that's the altitude, that's on the very far right. Those are zonal harmonics. Anyway, so we basically see the first thing that you see here is that convection, this is prograde, the blue is prograde, red is retrograde. I don't want you to focus on the amplitudes quite yet. There's some stuff that I have to work out before but I believe the shape of these things is right. So I see that, you see that basically power is all concentrated in sectoral harmonics and falls very sharply. By the time you get a S minus T of 10, you're done. There's no more convection. So everything is sitting sectorally confined, i.e. close to the equator. And so if I plot convective power as just as a function of latitude, and so that's what this plot shows. The horizontal axis is latitude, and these are arbitrary units because I've scaled the convective power. You can see that the prograde and retrograde, oh no, sorry, this is V theta, the blue is V theta, and the red is V phi. From inference, helioseismic inference, you can see everything is contained within or not everything, sorry. Plus minus 35 degrees here represents the full width at half maximum. So this stuff is squeezed into the equator. In contrast, these dashed lines here are numerical simulations, dashed and dot dashed lines. Those are everywhere. In fact, they're exactly the opposite. In fact, they diminish at the equator and they're higher at higher latitudes. So this means to say, and so this solid line tells you what differential rotation is. So if you think of convection, I mean, these are just modes being excited, convective modes being excited in a numerical box or in the sun. The sun is prefers a very different set of convective modes than the numerical simulations. So when you compare a numerical simulation with the sun, I mean, shouldn't you compare them only if the same modes are being excited? I mean, you would think that that's the first thing to do, and this had never occurred to me before, but it seems that numerical simulations are not the sun by any stretch of comparison. It's just a different set of modes. They're just looking at a different paradigm. I mean, I'm not even talking about parameter regime. There's just different modes of convection. At least this is what this suggests. Now, the second thing that I thought was really astonishing, also I should have realized a long time ago, is that no one ever plots this as a function of temporal frequency. And again, I would have, I point the accusatory finger at theorists who should have, in fact, looked at power as a function of temporal frequency in as much as they look at it as a function of wave number, spatial wave number. So this is what it looks like. So as I said, one of the nice results that Martin Woodard described in his theory paper in 2016 was how you could measure, using mode coupling, the variation of convective power as a function of temporal frequency. So on the horizontal axis here is sigma, which is the temporal frequency, the inverse time scale of convection. And the vertical axis is the velocity magnitude. And you see a very clean rise as a function of wave number, very similar to the spatial wave number that we've seen, right? So if you look at this again, harmonic degree, it's increasing essentially nearly continuously. It's the same thing is happening in temporal frequency too. If you look at numerical simulations, exactly the opposite is happening, i.e. the power decreases as a function of temporal frequency. And I haven't shown it here, but power decreases as a function of spatial wave number as well in numerical simulations. Again, very, very different systems, which brings me to the most, I'll get to the most critical point in a minute. There is no variation as a function of magnetic cycle. So I'll try to measure that as well. It seems that the error bars are too large, and it seems that the convective velocity magnitudes don't seem to change, at least on these large scales, as a function of the cycle. Okay, so that's the point that I wanted to make here. I wanted to show you the shapes of these convective cells. So I have inferences, as I said, of convection, toroidal flows. Here's a snapshot of convection. So these are V theta and V phi in HMI, and these are simulations. You remember, as I said, the simulations appear to show that the power is diminished in the equator and seems to rise at higher latitudes. That's exactly what's showing up here. So numerical simulations of diminished power, and the data show exactly the opposite, i.e. most of the power is sitting here. It looks like random noise. It's maybe random. I mean, it's something. There's a pattern there, but I don't know what fraction of it is noise and what part of it is real. I just take the raw measurements that I have. The raw measurements I have a significant component of realization noise, but I don't know what the noise is, so I can't subtract that noise. So that's why there's noise sitting in the midst of convection. But you can see that they're localized in the equator, and this is like everywhere. This power is everywhere. So I don't want to speculate that these are banana cells or not. I mean, if you look a little bit and you're imaginative, then you can kind of see banana cells here. But I don't know if they are or not. So I don't want to open up that can of worms. But anyway, so that's an important aspect. So the most critical thing I realized, as I said, it was a house of cards. This entire enterprise is a house of cards. So I can decide to put a cutoff at wave number. I can say I will go up to a certain specific spatial wave number or a certain specific temporal frequency. First of all, as I said, no one ever looks at temporal frequency. Every estimate, including mine, so I'm equally culpable, in 2012 when we compared the power of ash versus the power of helioseismology, measured by helioseismology. I didn't look into these details. I mean, in fact, someone's averaging over 50 days, another person's averaging over 3 days, everyone's doing something completely crazy. I mean, not doing completely crazy, but they're all completely different. And as Aaron said, these are apples and oranges. They're completely different things. So, I mean, so I'm embarrassed at myself equally. So that's the first thing that I want to say. So it's not like I'm pointing the finger, I'm also pointing it at myself. Okay, now having said that, depending on where you put your cutoff, I can integrate in my data up to 5 microhertz, up to 10 microhertz. I can include supergranulation. I can do so. So, I mean, I can, depending on where I put that cutoff, I can get any answer I want. Because the simulations, sorry, I should have put a plot of this. The power is going like this. Data, the power is going like this. Okay, so if I put the cutoff here, oh yeah, the simulations are much larger than the data. But if I put the cutoff here, data are much larger than simulations. If I choose the cutoff exactly right, they're both comparable. So I mean, so basically that I think was a realization that should have been obvious at the time, because it's true also spatial wave number. They're really different systems. So amplitude comparisons, amplitude ratios are an intrinsically flawed estimator of they're not a way to discriminate between one hypothesis and another. 5 minutes? I'm basically done. So that was a stunning but seemingly obvious realization to me. So that I have to kind of take back what I'd done some years earlier. So that's the thing that I wanted to say. Okay, so there's a lot of work that's continuing. This particular project is nearly at its end. But we haven't even begun to do poloidal flows, which there are many more technical challenges in doing poloidal convection. So we're kind of doing that. And as I said, we really do need to understand temporal variations, a significant part of it. The hope is that we excite the right modes of convection first, right? I mean, you go and talk about differential rotation, but what modes of convection are prevalent in these boxes? And can you get, so that type of thing, I think we need to understand. So yeah, there's this slide wasn't corrected. I'd given it some while ago. So this overestimate, so forget that overestimate is there. But this drop in power in large scales is a very real thing. It's seen at the surface, it's seen deeper down, and simulations can't do solar differential rotation. So the very last slide, this is an incredibly powerful technique. So what we're trying to do is we're trying to benchmark first the method against all these, as I said, standard candles. And so we're trying all of these things. The most exciting thing, just one last thing that I want to say, is that there's gravity G modes. G modes, we've seen all these methods which are, extraordinarily complex methods to try to estimate G modes. But normal modes potentially provide a very clean way of doing it. If you think of the radiative core as pulsing at 160 minutes with some non-hetero, it's a spatially anisotropic, because some, whatever, you have L equal to 10, M equal to 5 G mode, pulsing at 160 minutes. What it's actually doing is it's coupling two modes whose frequencies are apart by 160, or whatever, periods are apart by 160 minutes. So if you choose the right modes, if you go into the power spectrum of the sun, you say, I want to look at all pairs of modes that are apart in frequency, but exactly the right amount as that of G modes. Presumably they're being coupled if these G modes really do exist. So if nothing, it gives you at least an upper bound on what the amplitude of G modes in the deep interior are. I've seen all these different methods, but this is, in my opinion, the cleanest idea, cleanest way to try to get at something that's temporally varying and spatially anisotropic. So on that note, I'd like to stop. Thank you very much.
Yes, there's a question right here.
First off, a very nice talk, very impressive work. I really enjoyed it. Thank you. One thing that struck me, though, and I was a little bit concerned about, is the fall off that you're seeing at the high latitudes. And I wonder how much of that is due to the bad signal at the high latitudes. We really don't have good signal up there, and I suspect that that's contributing to at least some of that. Can you comment?
No, actually, I thought you were going to say magnetic fields. I mean, I'm not concerned so much about loss of signal because we know exactly. I model that. I mean, there's a leakage matrix. The fact that No, the loss of signal is not the critical issue, and the latitudes aren't so high. I mean, it's still 35 degrees. If you see this, it's still 35. This is 35 degrees. So I don't think this is zero. Here? I mean, I believe that it's decreasing. I mean, you're saying, is it because convective power is? I believe it. Yes, I believe it. But maybe we can discuss it at greater length. The only concern that I had initially was that this is also unfortunately correlated with magnetic fields. They're also sitting here, but I look at quiet years as well as I look at active years, and they're all basically pointing to the convective power sitting in this region. So, but we can discuss. Yeah.
Yeah, there was a question down there first. Yeah.
So when we used this method in 2011 and introduced the B coefficients, we thought that the leakage matrix is a relevant quantity here.
Mm-hmm.
So if you don't model the leakage matrix correctly, you introduce a lot of correlations and might introduce a lot of small-scale structure which is not in the data.
Yeah.
How sure are you that the leakage matrix you are using here is the correct one? Because it's probably a static one, not temporarily evolving, and therefore you might have.
But why would you think the leakage matrix is temporal? I mean,
there's a B coefficient. So a B
oh, you
angle,
mean the
B angle? The
B angle, not the B
time,
coefficient.
and that
Sorry.
introduces errors in your
Yes.
inversions. And if you don't model that right, and that is what we showed already in 2012,
We haven't modeled the B.
you have a problem with that.
Yeah.
And I agree with you that you are not sensitive to higher latitudes. So you have to have a.
But these are global modes. I mean, global modes are sensing the whole thing. I mean,
but inversions don't work there anyway because of the projection effects. Also,
Yeah, but
the rotation inversions don't work above 60 degrees. So I don't expect that you have any result above 60 degrees either, because we have the problem that we don't measure the modes.
I mean, 60 degrees is still pretty high. I mean, it's fine. I mean, I'm still at. I'm talking about here. I mean, it's decreasing pretty sharply. If you don't believe things at 35 degrees.
Yeah, but I would expect that this trend will happen because of projection effects.
Well, perhaps you guys should take this out to the parking lot and settle it. In the meantime, we have a question down here.
Thanks, Ravon. Very interesting talk. I have just kind of a couple of comments, and the first one is pretty general. I keep seeing this plot with the ASH results thrown up from several years ago, and then the phrase simulations has been used.
Yes.
I think it's very important that we. I'm sorry. We have to be very careful what we mean when we say simulations. Okay, and it's very important to know. It actually is important to know which region of parameter space those simulations are in. For instance, if you are near convective onset, for whatever reason, okay, you might still be fairly turbulent, but you're near onset. It is the equator, the modes at the equator that kick in first. And so your convective patterns are very sectoral. And so while your observations here disagree with one particular simulation from, I think, Hideyuki Hotta, that is not necessarily true in general. The other thing I'll mention is that this idea that models always show the power decreasing from large scales to small is not quite accurate either. As you move to more rotationally constrained states where the convective overturning time is much longer than the rotation period, you do tend to move the peak in the spectrum. And so if you're at a Rossby number of about 0.01, so the ratio of those two is like 1 to 100, you can actually get a peak in these convection models at L of 100, and power falls off toward larger scales when you subtract out the mean flows. And so I just want to say, I think we need to be very careful when we make statements that say, I don't know if simulations are even meaningful. I do agree that we should be very careful about how we compare amplitudes between these things, because models can only capture so many temporal or spatial scales. But I think some care should be taken
I agree.
in how we phrase these things.
I was going to point out that when I said Hideyuki simulation, we went through 5 different types of calculations. And so this is the final one we arrived at. So each one was producing something different. So I do apologize, that's accurate. You're right, it is very sensitive to what parameter regime you choose.
Any other quick questions? Okay, quick question down behind there.
So you talked about the angular scale and the frequencies of the modes. What about any signatures of asymmetry between upflows and downflows? For instance, the filling factor of upflows.
So these are toroidal flows. So toroidal flows are lateral. So
Can you go forward a couple slides?
Yeah.
Okay, so
These are again
you have a
toroidal.
V theta.
So you take the full flow field, and you project it into poloidal and toroidal.
Okay.
So
okay.
these are toroidal flows. I don't have access to poloidal flows in these measurements.
Okay.
Yeah.
Okay. Got it. Yeah.
Okay, well, let's thank Shravan again. And next talk here by Rick Egeland, who's going to tell us about where the sun is in a transitory stage in its dynamical. What was it said? I got to find it down here. Yeah, its dynamical evolution. Yep. So I don't see the. This one. Where did it go? Dancing and laser pointer. Okay.
All right. Hello, my name is Rick Egeland. This is some work that I've done over the past few years mostly with Travis Metcalf and Jennifer Van Seters. The title here is The Sun in a Transitory State of Its Dynamical Evolution. And I was thinking back to when the main point of this talk is its relation to Michael Thompson, and when I got in contact with him, what I was doing. So like any good modern graduate student, absolutely everything goes into a Git repository. So I have a complete history of everything I was doing. I was writing my thesis January 10th, 2017, just getting started. And here I'm writing, introduction 80% done, chapter interest, and I've got 3 months to write this thing. I got to write a book, and then I'll be able to graduate, and everything will be good. So the pressure's sort of on, and I'm a graduate research fellow here at HAO. And I'm probably up in my office there, and the phone rings. And what is that? I have a telephone. Like nobody calls me, right? And he says, turns out to be this guy right here, and he says, "It's like, hello, Ricky. I've been following some of the work that you've been doing with Travis Metcalf on this idea of a transition in stellar braking and how the implications it might have for the sun. Would you like to help me make a workshop for SHINE?" So that we can sort of discuss this and advertise it to the solar community that might not be familiar with some of these stellar observations. And I said, well, first of all, I was shocked, and some of the things in the introduction about how Michael, would talk to anybody and treat everybody the same. I completely concur with that. Why would he come, to me? I was just a lowly graduate student, but he's just treated me like a professional, like an equal. And I was like, yeah, sure, I don't know anything about making a conference session, but let's do it. And Michael, was very efficient. So it only took, a matter of a few days. And, he came up with this abstract to send, and I added some changes, and we modified it and sent it out. And it was this title for the session for SHINE, which is going to be in July of that year. Is the sun in a transitory state of dynamical evolution? And so it hinges on these observations here from Van Seters in 2016. The rotation in stars is older than the sun, rotated more rapidly than expected, given the previously observed schematic spin-down law that was empirically observed using stars younger than the sun. And that's a key point. So the work Metcalf and Egeland in FJ letters that there's a change in magnetic braking as well as other category transitions. The part that I highlighted here was, I think, Michael's interest in this. And he said this could relate to why it is so delicate to get a model of the sun that produces solar-like rather than anti-solar-like differential rotation, and to reproduce the rotation profile obtained from helioseismology. And we've mentioned this, especially Sascha Brun in his talk, about how it is a delicate matter to get this conical profile that was initially such a surprise from helioseismology compared to the rotation models that existed at the time. And if we remember back to Sasha's talk, it appears to be in a small parameter regime, which in some sense doesn't surprise me in a way that I'll explain later. But the general story is it's difficult to get these convective models to have conical differential rotation. And it seems to be near the point where stars shift to anti-solar differential rotation. And so this work from Gastine, 2014, tried to put a bunch of convective models onto the same Rossby number scale and observe that around Rossby number 1, which is where most of the modelers believe that the sun is near, it's close to this transition between solar-like and anti-solar differential rotation. So the session was accepted with some stipulations that we merge it with another session proposal that was dealing more with prediction of activity on the sun, some data assimilation topics. So that was from Irina Kichavelli and Malsumi Dikvadi. So even in the same building, we didn't really have any communication, but anyway, that's the way these things work out. So, so we merge it. We come up with a way to put these two things together, and the bit that deals with the solar transition and observed through the stars is highlighted here, and it's pretty much the same idea mentioned before. And so we had the session, and we discussed these ideas, and now I'll explain to you exactly what we discussed. These are actually from the summary of the session that I was charged with giving. The first, and so Travis Metcalf was the scene setting speaker. So if you've never been to Shine before, you've got this scene setting speaker who talks for 15 minutes, and then everyone has a discussion about these ideas and how can we move this thing forward. So this is what Travis presented. The critical observation comes from Kepler astroseismology, which gave finally, for the first time, a method to give precise ages for stars that are older than the sun by using their seismic modes in conjunction with the stellar structure and evolution models, which have an age parameter in them. And Kepler, giving its long photometric time series, is also an excellent way to get rotation. So you can start to plot the relationship between age and rotation. And what the surprise is that the stars were spinning faster, the stars older than the sun, so these are all G-type stars on this plot, were rotating faster than they should be expected to given this schematic braking. And that a rotational model could explain these observations if the spin down stops at a critical Rossby number of about 2. And that's where this dotted line diverges from the schematic law. So basically, a star is evolving its rotation, it gets to Rossby number somewhere around 2, and that stops, and then the evolution from that point on is dominated by the change in the moment of inertia, that the star is expanding and slowing down just through its expansion. So there's a wide band here, and that's due to the fact that there's stars of slightly different temperatures, and the gray band sort of covers the range of temperatures in the data. So the explanation for why would the braking stop? One leading hypothesis is that it has to do with the change in the large-scale structure of the magnetism that is responsible for the braking in the first place. This is a work from Ravel, 2015, that shows a couple of different magnetic moments, dipole, quadrupole, octopole, and the dashed line is the Alfvén radius, and basically where you have the high power, the oranges and the reds. Inside the Alfvén radius, you have strong rotational braking in that in that at that sort of latitude. And then you can see the alpha radius just shrinks for the octopole and quadrupole modes. And so transitioning away from a dipole would this sort of change in topology would be a way to change the braking. The other observation that holds up is the observation of rotation throughout the entire Kepler survey. So McQuillan published a catalog of about 34,000 rotation periods observed from Kepler, and it had this sort of sharp edge, as you can see in the data. So there's effective temperature on the bottom, and then the rotation period, and there's the sun sort of sitting next to this edge, and the blue line gives you the 95th percentile of the data, and Jen actually made a forward model in her stellar evolution code that includes rotation in the evolution code under two scenarios. One where the schematic braking occurs through the entire main sequence and beyond, and the other is a modified braking that stops at Rossby number 2.0. And you can see that that black line with the modified braking more or less corresponds to the 95th percentile. If there were schematic braking throughout the main sequence, for the hotter, for the sun-like stars and even hotter, you would expect to have a lot more population up there. So in 2019, she published these forward models, and they're basically constructed first with the galactic synthesis model, which is used widely in galactic astrophysics. Basically, it builds the population distributions of effective temperature and masses, and then she runs those through her stellar evolution code, and then it simulates the Kepler selection function. So basically, the bottom plot here gives you the simulated populations, and then there's the two lines. The dark red line are the observed from Kepler, the 95th percentile, and then the upper dashed line is what you get from just unmodified braking. And then there's two sort of explanations for why this, you could see why this sharp edge may exist. The first is just that there's a detection limit, that there's some transition, temperature dependent, where the surface features that give you rotational modulation just become too small. Maybe they fall into the noise of Kepler, and you can't measure rotation period anymore, and that would give you a hard edge. And again, at this critical Rossby number, and then the case where there's actually a change in the braking is given in the bottom panel. They look very similar. One of the main differences is there's a pileup of stars sort of near that edge, because if stars sort of stop braking, then sit there at a certain rotation period for a long time, you're going to get a population density, which isn't able to be seen in the observed distributions, and it's probably because the stars are not parameterized very well. If you add this sort of 200 Kelvin uncertainty in the effective temperature, you can blur that out pretty easily. So that's another observation there. And then Metcalf and our interpretation of what this means is, in terms of long-term activity, is that when you look at this Bohm-Vitézi-like diagram of cycle periods versus rotation period, the sun had this sort of peculiar location. So this is the original publication of it, where it sits in the middle of these two activity branches, and it's sort of inexplicable. But in this interpretation, the sun has stopped rotating, but the cycle continues to evolve. So points continue to go upward in this diagram. And there are other sun-like stars that, that also follow this sort of pattern. And so this is the hypothesis that we're working with. And it basically follows this story that that stars, begin their lives very active, almost chaotically varied. They settle down. Everything here is on the same scale. This is 50 years of HK observations from my thesis. They become well behaved like the sun, and then the dynamo just dies out somewhere around this transition period. And so we discussed these things at the workshop. It was very fruitful discussions. It was nice to have people with different views. A lot of space weather people, wind people. People that, and I think it was very successful in that regard. And I'll just go quickly. How much time left? Huh? Minute or two. Okay. So we asked what additional observations would test this hypothesis that this thing is real. First of all, it appears to be in the older data that from gyrochronology. Here on the x-axis we have magnetic activity, and then the difference between two aging mechanisms, one using the chromospheric HK data and one using gyrochronology. And beyond the activity level of the sun, we start to, this is measured in standard deviations of either of those two methods. Beyond the activity level of the sun, the stars start diverging. So this is from a Barnes paper which is establishing gyrochronology, and even in that data set, you can basically see that the stars are rotating too fast as they get low activity. A more recent result that's quite interesting is from this system 94 Aquarius. It has been observed in Mount Wilson. So we have rotation periods from the HK time series. It's a multiple system, but you can basically ignore the AB component because it's so faint and it's outshone by its subgiant companion in both these calcium and in the TESS observations. And so for the interesting thing is the AA component, the subgiant. So from HK, you get a rotation period of 46 days. You get from the TESS photometry a very nice astroseismic characterization of its properties. So it's a subgiant, 2 solar radii. It's more massive than the sun, and you get its precise age at 6.2 gigayears. And the question is, if this thing was doing the schematic spin down for its whole life, what would its rotation be expected to be? The answer is 78 days. Whereas if you involve, so this is a slide from Jen Van Saters, if you do the modified braking, you would expect 48 days, which is what is observed. And these are widely separated. So subgiants are an excellent test of this. I'm gonna skip this one. We discussed what new simulations should be conducted. There hasn't been a lot of simulation work, I would say, to connect this scenario. It's very difficult. You first have to basically get the entire dynamo right, and then couple it to, a wind, a stellar wind, and get of all of that. But it has been a motivation for this Cameron and Schuessler work that uses the fact that if the sun is near a critical point, where the dynamo becomes subcritical, then you can use this nonlinear model, so in a very general way, which it turns out works in the same way with the Babcock-Layton dynamo model. And using that fact alone, you can reproduce some of the long-term statistics, for instance, like the occurrence rates of grand minima and things like that. Finally, how accurate and precise are estimates of the current angular momentum loss from the sun, and how might these be improved? This generated the most discussion, I would say, at SHINE. And Travis and I, whenever we go around, we're like, okay, what's the current torque on the sun? And nobody really has a super good answer for us yet. So I think this is the work to be done. But basically, our conjecture is that the sun has already stopped rotating. So if we could get a measure of the torque on the sun now, just assume that torque continues for the rest of its main sequence lifetime. Is it going to move up in this diagram, or is it going to be approximately zero, right? Is the rotation really stopped? And so that's the conclusion. I'll just say it's been a pleasant surprise and honor to work with Michael Thompson on this session. I think it was very successful. There's more evidence coming, especially from the TESS mission about activity, rotation, and I'm sure there'll be more interesting physical mechanisms to explore related to this idea. Thanks.
All right. I was shocked to hear the sun has stopped rotating. Anybody got any questions?
Oh, sorry about that. Changing rotation, of course.
No questions at all here. Remarkable. So it hasn't stopped rotating.
No, no.
No.
Not
Okay,
so far
good,
as I know. I
because
didn't
was
look
kind of
today.
getting worried about that. Well, it might have. Maybe I'll go check it out in the next break. Okay, well, in that case, we can catch up on the schedule and move on to the next talk. And oh, this time I've got to be careful. This is Savita. Much longer title, it's more than I can remember. Surface rotation and magnetic activity of solar-like stars, impact on seismic detections. So go ahead. So that's advance and that's laser.
Yes. Okay, can you hear me? Yeah? Okay. This is not the one. Okay, so hi everyone. So today I'm going to talk to you about some work we've been doing on studying, measuring surface radiation and magnetic activity of solar-like stars and how it's impacting seismic detections. So this is a work. This. No, it doesn't work. This is better. Okay. So this is a work that we've been doing with a large collaboration, mostly with Angela Santos and Rafa Garcia. So here I won't go back too much about general chronology, as Ricky already talked about this a little bit, but I just wanted to remind you what Skumanich found with the study of two young clusters and the sun and how the rotation and magnetic activity decreased with the age of the star, with a square root of the age of the star. And later there was also some dependency with the stellar mass that was shown, where the stars that are more massive than 1.25 solar masses seem to rotate faster than the one with a lower mass. And Ricky already also talked about the results from the Van Seters analysis, showing that the magnetic braiding stops for a given Rossby number. But we are still interested in measuring surface radiation of a lot of stars to better constrain what's happening with the angular momentum of stars along the age of the stars. So given all the data that we have with Kepler, we've been studying the photometric data, where because you have active regions on the visible disk of the stars, you can see the modulation of these active regions due to the rotation of the spots of the star. So you have different methods to measure the surface rotation. You can use the classical periodogram, do some time frequency analysis. This is a wavelet analysis. So you have the period as a function of time. And you can also compute the autocorrelation function, which has also been applied with thousands of stars already. So here I just wanted to show you some simulations that were used to test these different techniques. So this is a paper by Aqr collaborators in 2015, where they injected 1,000 sinusoids, simulated sinusoids, into real Kepler light curves. So here you have on the y-axis the determined period from different pipelines, and the x-axis is the true rotation period. And you can see that for most of the pipelines, we recover the rotation period, but some of the pipelines are better than the other ones. And our pipeline is the one here, the CE1, which is the combination of the time frequency analysis and the autocorrelation function. And it was shown as to be one of the best methods in terms of completeness and reliability. So this is the technique that we've been using on the Kepler data. And another thing that we can measure using the photometric observations is having a proxy of the magnetic activity, because we are measuring the rotation through the presence of active regions. It means the star is active, and just by measuring the standard deviation of the time series, we can have an idea of how active the star is. And this SPH, what we call the SPH, the photometric S index, has been compared to other classical proxy for the sun, where we used the Virgo data to measure it, and we showed that by comparing it to sunspot number, sunspot areas, the flux at 10.7 centimeters or calcium HK, we found a very good correlation between the SPH and this classical proxy for the solar magnetic activity. So we validated the SPH as a good proxy. So let me start first with the K and M dwarfs that were observed with the Kepler satellite. So this is a work that was done by, and mostly done by Angela. I think now it's not in press, it's already out. So we started with a sample of 26,521 targets. And we actually first removed some polluters in the sample, like eclipsing binaries, red giants, classical pulsators, some also close binary candidates. And from there, we analyzed different light curves produced by different techniques. So one of the calibration was done with the CADAX pipeline, where we used 3 different filters, 20, 55 day and 80 days. And then we also used the PDC map, which are the light curves from the Kepler science team. And this is a way to compare that we have the real rotation periods when we use these different light curves and calibration. So this is the results of the analysis of the 26,000 stars. So we managed to get reliable rotation periods for more than 15,000 stars, which is a yield of more than 60%, which is pretty good. So here you have the rotation period as a function of the effective temperature of the stars, the frontier between the K dwarfs and the M dwarfs. You can see that in the M dwarfs we also have some slower rotators. And from there we also computed, so we compared these results with the literature that's already present. So basically it's the McQuillan and collaborators paper where they had many detection of rotation periods. And so we had 70% of the stars in common with that paper. And we found that we had a very good agreement with the rotation periods that they had in common with us. But with our analysis, we found additional rotation periods that were not reported by McQuillan. And this is the case for more than 4,000 stars. And if you look at the diagram on the right, where you have the distribution of the Kepler magnitude for these stars, you can see that in our work, we managed to have rotation periods for fainter and also cooler stars compared to McQuillan. So we are able to go further now. And here I'm just showing the SPH, so the magnetic proxy of the stars as a function of the rotation period. In green, you have the lines corresponding to the SPH for the sun at minimum activity here and maximum activity. And you can see that the K and M dwarfs are actually usually more active than the sun, and also that the faster rotators are more active than the slower rotators, which is what we would expect. So now we move on to the G-type stars and GF-type stars and subgiants for which we had detected oscillations with Kepler. So this is a sample of 540 stars, and we detected surface rotations for 310 stars. These are represented in this HR diagram here. And a few things that I wanted to point out. So here you can see that the hot stars are the ones that rotate faster, which is what we expected. And then you have the subgiants that have some slower rotators. And these rotation periods were actually the base of what was used for the Van Seder's results. So this led to the discovery of the magnetic braking of the star. And the other thing I wanted to point out is that this was also some beginning of the collaboration we started with Michael Thompson, with Angela, where we wanted to use the surface rotation to constrain the rotation inversions to see how it was changing the results if we were not using these constraints. And so I invite you to look at the poster 32 here. Okay, and so these were for the stars where we had detected oscillations, but we have much more stars observed by Kepler, FG and dwarfs and subgiants. So we are in the process of analyzing, so it's actually, I think, 100,000 more stars that we need to analyze. But here it's just a preliminary results of the analysis of 70,000 stars, for which we have, from the automatic analysis, 19,000 stars with rotation periods. And now we are implementing machine learning techniques to avoid having Angela to visually check all the light curves. So this is a work in progress, but we were happy because we already have the same number of stars as the macquillan, but we should have many more coming up soon. So now I just want to move on to another sample of stars. So I talked to you about the rotation period of the stars where we had detected oscillations, but we also had some stars where we didn't manage to detect some oscillations, even though we had short cadence data. So during the Kepler survey phase, there were more than 2,500 stars that were observed in short cadence as part of the working group 1, and the oscillations were detected only in more than 500 stars. So why are we not detecting oscillations for the other stars? And Chaplin and collaborators did the study in 2011, and they blamed magnetic activity, which is a good thing to do, because we know that magnetic activity suppresses the amplitudes of the modes, and this is what Angela is going to talk about tomorrow. But we noticed that in that sample there were some red giants, some classical pulsators, and we also detected new oscillations using the latest data release. So here you have the nature diagram showing all the working group 1 survey stars in gray, in both here. Here the oscillating stars, and here our sample of stars where we had removed the pollutions. So one thing we first did was to compute the predicted maximum amplitude of the modes using some scaling relations. And then we also computed the noise at high frequency in the power spectrum density from Kepler, from the short cadence. And we computed the ratio. So the ratio of the predicted amplitude and the noise as a function of effective temperature is presented here. And you can notice that all the oscillating stars have a ratio above 1, most of them. A few are below, but it's just a handful of them. But we still have many non-oscillating stars with a ratio above 1. So for the next step of the analysis, we selected only the stars where we were expecting to observe the modes, and also the same region in the HR diagram as the oscillating stars without the subgiants. So this led to approximately 500 stars. And then we analyzed the surface rotation of these stars and found 323 stars with reliable rotation periods. And we computed the SPH, here the SPH as a function of the rotation period. And we found that only 32% of the stars where we didn't detect oscillations are above the maximum SPH for the sun at maximum activity. So magnetic activity is not the main reason why we are not detecting modes for these stars. So we looked at a few other culprits. The first one is metallicity, because metallicity is expected to have an impact on the suppression of the modes. So lower metallicity will suppress the amplitude of the modes. So here we had high resolution spectroscopic observations for some of these stars with apogee on the left, and with LAMOST, this is low resolution spectroscopy with LAMOST. So you can see that some of the stars with low activity in blue do have low metallicity, but some have high metallicity. So we can explain part of this non-detection because of metallicity, but not the other half. And also we don't have many stars, so we would need to have additional observations to really confirm this. Another thing that can have an impact on this non-detection is, well, this is not the non-detection, but we also need to take into account that the SPH that we are measuring depends on the inclination angle of the star. So if the star is too inclined, we won't be able to see all the active regions, and the SPH is just a lower limit of the magnetic activity. So I looked at the inclination angle of the stars using the V sin I from the apogee observations. Here again, we don't have many stars. It's low, but less than 100 stars. And you can see that the inclination is more or less all over the place, and the error bars are pretty large, around 20 degrees. So this is not something that can be used yet unless we get more observations. Then another thing that can have an impact on the amplitude of the modes is the binarity, because sometimes the presence of a companion through hadron interaction can suppress the modes. So we looked at we cross-matched our sample with Gaia binaries and also interferometer observations, but we didn't have any stars to confirm this. And the last thing that can that can explain why we don't detect the modes is just that we are overestimating the predicted amplitude of the modes. So this can be due to the radius that I'm using, which is mostly coming from photometry, not STSW, so it can have an impact, and the effective temperature can be also wrong. So this is also something to take into account. So as a summary, so I showed you that we managed to detect for the moment rotation periods for more than 34,000 stars. 44,000 stars, yes, and hopefully we'll have more coming up soon. And we still have to explain what's the main reason for not detecting oscillations in some of the solar-like stars, while magnetic activity can be one culprit, but we need to see what's the reason for the other ones. So I thank you for your attention.
So let's see, do we have questions? Surely somebody must have a question here. No, everybody's waiting for the public talks. No, there's a question. Yes.
Hey, Savita. So you got more rotation periods detected. Do you find any more evidence of the long period edge changing position from the McQuillan sample, or is it sort of in the same place?
So this is very preliminary. So which one are you talking about? This edge here? So we do have the subgiants here. I think these are the subgiants that we find, but otherwise we didn't compare. And yeah, we didn't visually check yet many of them. So some might be removed and we might add more stars and the machine learning will do more. So for the moment, I won't say anything on that yet.
And now that you have that slide up, there seems to be a gap in effective temperature. Is that an observational bias?
Yeah, this one is known. It's the way the temperature was computed for the cool stars and for the very cool stars and the other stars. So it's a known artifact. Yeah.
So I have a follow-up on the same slide. So there seem to be some of kind of a step function at the top and some very vertical lines. Can you explain what those are?
Around here, I guess you're talking about this one.
Yeah, they're in the bottom of the same place, and a little bit to the left at 6,000 Kelvin, you again have.
Yes. Yes, so this is because we haven't analyzed all the stars yet. So we divided them into chunks, and then we realized that we were missing stars in between, and we will fill these gaps. It's just because we are doing subsamples analysis and we missed some stars, and Rafa is still downloading some new data and calibrating them. So it's yeah, that's
Okay. Jan wants to ask a very quick question. Very quick.
So it's really almost a paradigm shift, isn't it? to say that the magnetic fields are not a cause of the non-detections. So how does that affect our likelihood of seeing oscillations in young stars or pre-main sequence stars even?
Well, if they are
I could also address that
active.
question to Bill, who's been pushing the magnetic
See if the speaker might have an answer to it.
Short
Well,
question, long answer maybe.
I would say that if they are too active, then yeah, it will be less.
It's interesting.
Yes, yes.
With this especially because we have lots of stars potentially.
Okay, well, in that case, I guess we'll thank Savita again. And as you all know, there'll be two public talks in about 20 minutes. And of course, everybody's invited, but they are public talks.
Yeah, so there'll be a public talk. The public is going to be in here in 20 minutes at 5 o'clock, and we'll have the public talks from Yuri and Yvonne. So, and then following that, there'll be some refreshments and food. And Yurin, I understand you're going to be chair of the session, the public lecture session. Excellent.
That helps. So welcome to this session. For those of you who are not taking part in the conference that we have these few days, let me just mention that this is part of a conference to honor the memory of Michael Thompson, who passed away last year, almost a year ago. Michael was a very important person in Boulder. He was also a very important person elsewhere. But in the last 10 years, he was in Boulder, first as director of the High Altitude Observatory, and then as deputy director of NCAR and chief executive officer. I have no idea what that means in a semi-academic setting, but
operating officer.
Oh, chief operating officer, very important. I still don't know what that means, but that's okay. But I also have to mention that for me, he was a very close collaborator. I'm Jørgen Christensen Dalsgaard from Aarhus University, and Michael was my first postdoc, and he had his first postdoc with me in Aarhus more than 30 years ago. So we've been close collaborators and close friends, basically, ever since. So for all of us, it's been a huge loss, and we still haven't completely come to terms with that. But a conference is a very good way to remember Michael and carry on his work, and to help us remembering Michael and see what the future is of his work. We have these two public talks this evening, and the first one is given by Yuri Tumra from the Colorado University on Only a Star. So Yuri, please.
Thank you. Well, good evening, or good early evening. So, although I may be bringing coals to Newcastle, as the British would say, bringing to quite a few members of the audience things they basically know about, but I'd like to also share what is the background and motivation of the work. Mic is okay? Lift it up. I'll hang it from my beard. Fine. Thank you. So we'd like to make it palatable as to why we are gathered as a scientific community, what motivates us. I will talk about some of the properties of our own star, the sun, our nearest star, which has a distinction that we can actually see it in great detail. And then our second speaker, Yvonne, will speak about what we're able to infer remarkably about other stars, having been partly trained on some of the possibilities that the sun offers. But there are also many other types of stars with some remarkable properties, and they outnumber us by zillions and zillions. If we think that we have our nearest star, well, our galaxy has about 400 billion stars, and to those who know some things about cosmology, our galaxy is only one of maybe about 200 billion. So when it comes to the question, are we unique? Probably not. So what's our story? And the main issue is we're celebrating these two people. And they shared with us, I mean, the man on the left is Michael, of course, and the lady on the right is Kate. And they're English or British because they're drinking beer where others could be drinking also wine. Michael is an Englishman in the sense that he was born in Nottingham, a region well known for Stilton cheese, among other things. A few other counties also qualify, apparently. But he went to the University of Cambridge, as did Kate. And Kate's boyfriend introduced him to Michael, and they eventually got married. That's the story. And then Michael, after getting his degree in Cambridge, decided that, as Douglas Goff told us, his later supervisor, that Michael felt that he should do something in industry for a few years, and then found that to be a little bit boring, and came back and did a PhD in Cambridge with Douglas Goff, who at that point was very much interested in shakes and quivers of stars and astronomical fluid dynamics and things like that. So that's the background. And Michael also became the director of the High Altitude Observatory about the time when the 75th year of this august institution was being celebrated. Now, what is helioseismology and how does Michael play into this game? Well, helioseismology, or HS that I've said here, is really something about acoustic oscillations, basically sound waves that are bouncing inside the interior of the sun in great numbers. And we're able to use them, although they're mostly bouncing around inside, some of them leak into the atmosphere where we can detect them. And this has become the subject of this title. Seismos, of course, is shakes and quivers in Greek. Ology is the study thereof. And again, the supervisor pointed out that it should be Greek to Greek. So we made it helioseismology, as it bears on the sun, rather than solar seismology, which seemed more palatable, maybe, at least to me, but I'm only Estonian in background, not Greek. But what we have discovered is that the inside of the sun is resonating quite selectively with about 10 million notes. And they occupy different portions of that star, and we can use something about their properties to infer, to essentially image things about large-scale flows and structures within the inside of a star, which we otherwise cannot see. The light does not get in. We just see an opaque fog at the surface, which we call the photosphere. But looking inside is made possible by acoustic modes. And it's somewhat similar to what we do with our own Earth, where the earthquakes are able to set partly the Earth oscillating, shaking, or we can see direct signals from an earthquake site to where the seismic measurements are. And that's really the only way that we're able to make some direct measurements of the inside of the Earth. We're able to use quite a few of the techniques that they had developed to be able to carry it over into a star. The distinctive difference is that we'll show you that the sun is shaking all the time because somebody is pounding the top of the sun with about a million little hammers all the time. So the sun is quivering constantly, whereas the Earth, you got to wait for the big bangs to come along. And we say, you know, it's a 6.4 on the magnitude scale, and then everything shakes. Those are reasonably infrequent and probably very good that they're infrequent. Now, there's a whole bunch of mathematics that goes along with trying to use information from these resonant modes. We have to combine the information in some ways, and we've come to call it inverse theory. There's a bunch of mathematics with it. I won't expose you to that. I mean, it's not dangerous. It's linear mathematics, but more significantly, I'd like to show you how it is that the sun has come to resonate. What's our evidence, remarkable evidence for these shakes and quivers, and then what do we make of it? And above all, why the heck do we even work on this? And so Michael's contributions in many ways was both for devising and applying these so-called inversion methods to using a large fraction of these modes to make inferences about what large-scale flows and properties of the sun in the interior. It was a fairly major effort involving lots of folks, but he was particularly exuberant and friendly and available to help carry these things out. And above all, he was, being a fairly gentle but enthusiastic person, was able to share what he thought were theoretical insights that could be gleaned from this in a very collegial fashion. Now, just a little bit of history. Many of us have been, including I and my wife, Linda, have been friends and colleagues since we first met Michael in about 1988, when Kate and Michael came to Boulder after having finished his PhD thesis in Cambridge and then worked briefly with Jan to be a HAO postdoc. And the timing was such that Robin, who's also here and a scientist, decided it was an appropriate time to be born. So Boulder Community Hospital, it was also an intense competition with Mark Rast, who had a son being born, I think a little bit later. Robin popped out first, but shortly thereafter, in 1990, we were able to arrange for a 6-month focus program at the Institute for Theoretical Physics in Santa Barbara. Most of us lived there. And we were able to, also in some earlier working groups, put together essentially quite a bit of the machinery that would be needed once the floodgates opened on observations. But interesting enough, not only was Santa Barbara there, but Kate and I did some counting of how often were they in Boulder before eventually Michael became the director of HAO in 2010. And the answer was they spent at least 13 plus maybe a little bit more summertime visits of about a month apiece to Boulder. So I think by both the birth evidence and by 13 months, 13 years at least visiting Boulder, plus maybe a little bit more, he probably qualifies almost as a Boulder native. So we could put that on the car, native. And so he functioned as a director too competently for about 3 years and then was snared off to become chief operating officer, whatever that is. That's a guy who really makes things work, and associate director of NCAR, until Michael died, sadly and very, very suddenly in Japan, on October 15th, a year ago. So why do we bother with this sort of stuff? And the answer is, we're next to a star, we're able to cut through it, and below the visible surface, which is, it's invisible to light beyond that, it's just a fog, we know, at least from theoretical considerations, that there's a roiling, boiling section occupying the outer 30% just below the surface, which we call a convection zone. The sun makes its energy by nuclear burning in the core, occupies about 15 or 20% in the radius. Radiation carries it out to about 70% of the way out. And at that point, it becomes a little bit too opaque. Radiation can't get out efficiently enough. It changes its structure and becomes roiling, boiling. And the rolling boiling scales are such that they're very small near the surface and larger scales in the middle. It's the larger scales that can sense the fact that the star, when it was assembled, was rotating. When the sun was first probably assembled, we think it might have been rotating a fairly fast clip, like of the order of 100 kilometers per second. It can just kind of hold itself together, but then it's been losing its angular momentum by its winds, and now we're going at a leisurely 2 kilometers per second. Pretty fast still. It would give you, if somebody, one of the radar vans in town would see you going at 2 kilometers per second, you'd get a speeding ticket. But they would be probably not prepared to have you move so fast before the flash goes off. Perhaps some of you have experienced the speed bands. They're in fixed locations. So the big issue, though, is this deep shell of very turbulent convection does something where, if it's in the presence of strong rotational effect, it leads to differential rotation. And we'll see that what comes about is that the equatorial region of the sun rotates once in about 25 days, the polar regions in about 33 days. We call this differential rotation. So one of the questions is, how is that differential established? It isn't like you put it together and then you walk away from it. This thing is churning away and somehow is maintaining that almost all the time. Now, that's the star. Why do we care? Well, fortunately, that star isn't changing very much. We and the star have been around for about 4.5 billion years. We're about halfway through our evolution together. Of course, personkind has been here for a very short period of time, maybe 40,000 years doing something, 100,000. But the remarkable thing is that this object both rotates and has magnetic fields. So what's our evidence for that? Well, if we take $1 billion spacecraft and take pictures, and you can get them online, and ask, what does the sun look like over 2 days? The defect regions that are here, yellow and orange, are regions of fairly strong magnetic field, and we're able to measure it with some spectral lines. You see some mottliness everywhere, and it looks like somebody is rotating it. That's the solar rotation. On these pictures, you can't see the differential rotation, but the sun, at least at the surface, is magnetic. And these things are places where magnetism has popped out, and we call them sunspots. And they usually come in pairs of a north pole and a south pole as they come along. But if we looked at it exquisitely from the ground and said, well, what does it look like? Well, it looks like Van Gogh's sunflowers. So this is one of the details of a particular sunspot. It has some companions. The center is called umbra because it's that dark brown color the painters use. This is the penumbra, not quite, but it shows things about magnetic field coming out of a great big patch. And the fields there, although the average field of the sun is 1 Gauss, the fields there are about 4,000 Gauss. And we're sitting, in fact, in 1 Gauss field because that's about the strength of the Earth's magnetic field. But mixed in with this are all these little speckles, and that is called granulation. That's the very small scale convection that is going on. I'll show you some movies of it in a moment, but that is the thing that is in fact making the sound. It's very fast overturning motion that lasts for about 5 or 7 or 8 minutes, and then it gets replaced by something else. But it's like a series of pistons hitting both the inside and the outside of the star. And we've known about them for quite some time. We call them 5-minute oscillations. We call this granulation because they look like little granules. However, if we look at the sun in a different way, in ultraviolet, by climbing ourselves above the Earth's atmosphere, here are the waning days of the last century, 1999, and we see much more structure, not so fine stuff, but we see stuff. And this is a time when the sun was particularly magnetically active. Our concern was that once we got to essentially this thing ticking over to, this is Christmas Day just went by, there were these dark things coming about. Was it threatening? Above all, what was really threatening was that all of our computers were running with only 2 digits for the year, and we thought the entire computer system and banking system would collapse. It almost did, but thanks to the lots of internet connection and our colleagues in India, they fixed enough of the business software that we survived. However, it wasn't very propitious to have this great dark thing, which we call a coronal hole, bringing us into the first year. What's the message? Well, mostly the sun at other wavelengths is really active, and these things that are these bright points are in fact places where magnetic fields have come out, looking benign when they're sunspots, but they actually in the atmosphere, which is much hotter, much more tenuous, lead to expulsion of things, and they can in fact lead to some real expulsions that we see with, again, other satellite images, which we call coronal mass ejections. And some of these may involve about several hundred or 1,000 billion tons or so of plasma, and depending upon where it goes, it can shut down satellites in space, it can power up our big electrical transmission lines in Quebec and shut down Canada. It can do things. And so the sun, although it's benign in the visible, hardly ever changes. In the magnetism, it changes a lot. And so one of our driving questions is, do we understand where does the magnetism come from? Who makes it? And it's clear it's not made at the surface, it's made on the interior of the sun by some, so we call it magnetic dynamo action. The churning motions of this plasma build magnetic fields, but some with very intense structures. And what other evidence do we have? Well, when we take a series of pictures of the sun in a particular ultraviolet line called 304 angstroms, it's quite clear that from 1966, as we go around with these pizza pies, the sun looks quite different. And where it's really bright is where we have magnetic activity, and it could have these ejections and other things. And we've shown 11 years here because it actually suggests from other things that the sun has roughly 11-year cycles, which we call, if we look at the sunspots or activity, we see it comes and goes. The sunspots, so-called early in the cycle, appear at about 30 degrees north and south, and then as the time proceeds, they get closer and closer to the equator, and then poop out and start again. And these are called butterfly diagrams because they look like butterflies. And the color is just represents how many sunspots there are at any given time. But the other measures is that if we again ask how many sunspots are there, occupying only a small fraction of the entire surface, it comes and goes. So why does the sun, which is a highly turbulent system, why does it have 11-year cycles? How does it do it? Why is it that there's some sort of orderly breakout of sunspots at certain things, and then they get closer and closer to the equator, and they do it again? So magnetism gives us a very different view of the star. It looks benign. We can only see a few defects, and sadly, Galileo was ostracized by the church because he saw defects in the sun, and the sun was supposed to be perfect, a sphere, and you shouldn't question. And of course, there are small other things like the Earth was the center of the universe, and that came into question. But so, what's with this subject of helioseismology? If we take a cross-section cut of the sun, there are different waves, some that are able to be somehow made near the surface, and they just noodle below the surface. There are others that go much deeper. There are even others that go right through. There's some waves, if you make it here, and it gets to the other side in 55 minutes, because mostly the speed of sound is about 7 kilometers per second at the surface, and it's about 200 here. And that fact that the speed of sound changes, and if we send a sound wave in, different portions of this, the wave travel in a slightly different direction. I'll show you that in a moment. This is one of the global acoustic modes. We would love to also have the sun have some gravity waves, which are below the convection zone, and they look more like their signatures that of a rose. But we've tried awfully hard, and so far we haven't been able to make unambiguous detections of them. So what is it that's driving these things? Well, again, here's a high resolution image from the ground of what the granulation looks like. This is from La Palma in Tenerife region. Granulation is here in the background, but you see it's just kind of throbbing away. And any given sort of bubbling cell, if we looked at it, it can be recognized for just a little while. And the dimension of these cells is of Colorado size. They're about 1,000 kilometers. We say 1 megameter, or 10 to the 6, and so is Colorado diagonally. So each of these cells is about like Colorado. But there are about 1 million of them on the solar surface at any given time, and they just turn over and throb, and they're actually quite fast. They're going at about a kilometer per second, and some of it is convection, but some of it is also makes sound. Some comes into the atmosphere, other goes inside. So what do we do? Well, in order to actually make some sense of the throbbing of the sun, we had to build observing systems that could basically see all of the sun and see it nearly continuously. So one of the efforts that the National Science Foundation supported was called the Global Oscillation Network Group, that built a series of observatories around the world that could look at the sun almost continuously. Good sites were chosen, and they could look at how various pieces of the sun were moving up and down, so-called Doppler measurements using spectral lines. And the business end of these things was something like this, little cubes. Here's a 25 cents for comparison. On the other hand, each of these were about $30,000. And you put a bunch of them into these shelters. And there are 2 of these shelters here on the East Campus of CU, because the National Solar Observatory that assembled this gong network has now shifted to Boulder. So you can visit them if you like. But more seriously, because it doesn't have the interruptions, we were able to talk NASA and ESA into assembling a spacecraft called the Solar Heliospheric Observatory. And it was put at the L1 Lagrangian point, where the pull of the Earth's gravity just balances that of the sun. It's kind of a saddle. You can sit there, but you don't have much of a movement during the course of the time. But you are about 1 million miles away from here. So you need big space network antennas to be able to bring the signal down. So that was both GONG and the SOHO spacecraft. And the thing that became the helioseismology instrument is one of these boxes here. Here are people for size. And we operated, but this was able to provide essentially 1,000 by 1,000 picture of the oscillating sun every however much time we wanted, 40 seconds a minute. And the typical period is about 5 minutes, so we could resolve things fairly well. And we continued that from 1996 to April 2011. GONG started in 1995. But these were big investments of people, both money, but also really effort to build and maintain them. And an entire group was built around it. Whoops. No, I don't want that. Away. And then this was replaced by something where the people got smaller, or maybe this got bigger, or maybe they were really Darth Vader people. I don't know. But we launched something in February 2010, but it was much closer. It was basically like in geosynchronous orbit, so we could use television technology to bring bags of data down. It was a tilted orbit, so it didn't get in the way of the Earth, and that is operating right now, also called the Solar Dynamics Observatory. So those are the 3 major tools plus smaller experiments that provide us information. What do they give us? Well, if we go look at the surface of the sun, here's a small piece of the sun, just 20 degrees across, and it looks like it's a throbbing waterbed. And that is the signal essentially of the oscillations coming through. There's some convection too, but these are throbbing things. And what we're seeing is the overlap of many different scales of oscillation, and they have this sort of pattern. And if we said, well, what does the sun look like in the whole? That's the whole image. So that's our business part. I mean, that's what we can kind of see, we capture it, and then we have to figure out what's the cause of these things. And the cause of it is that we think that of the 10 million modes or so, one of them looks like this. This is the sun, it's round, where it's blue or red is given time, piece of the sun is moving up and down. And it varies also in depth. We cut away a piece of it. Here's the convection zone. Here's the radiative interior. But the way this resonant mode, this particular resonant mode is throbbing, there's a pattern like that. And there's a very large range of different resonances that can come about. And each one of them has a different distinctive tone. And we have some opinions about what they might be. And we can use the tones. We can also use certain Doppler shifts of these tones. And if we take about a month or two of data where we take pictures every minute and then analyze them and ask how much belongs to each kind of a mode, and then say, so what's the underlying story? The answer is, if we said, wherever it's red, we have lots of power. What's here is how many wiggles there are on a great circle. We call it the angular degree of the mode. So if it's 100, then if we go on a great circle, it'll reverse its sign 100 times. And on the vertical, on the other hand, is to say, how does it vary in time? And what is remarkable is that throbbing surface that we looked at when analyzed shows that there's a lot of power on very discrete, distinctive ridges. And we can relate them to what are the different kinds of oscillations that would be occurring inside the sun. And so this is data from a few months of data from MDI SOHO. Theoretical predictions are on the right. And what is remarkable really is if we study this thing in great detail, again, here it looks like one of these power diagrams, horizontal structure, harmonic degree and frequency. But when we zoom in on something, it isn't that it's just a continuous ridge, it's distinctive little archipelago of frequencies. And that says that there are some really selected frequencies or modes that we've come into resonance, and in between there's just a bit of spill because we can't see the entire sun simultaneously. But we can measure these frequencies very accurately and then do something with it. And what Michael was involved in was to help provide the machinery with which we do something with it. Now, why does any of this occur? Well, mostly because if this is the surface of the sun and somebody is throbbing and making sound waves, they begin to sort of travel inwards. Depends upon kind of the angle of their propagation. But these are essentially the wave fronts that are moving in. And the reason why they get turned like this is that the sun gets hotter. It's about 6,000 Kelvin here and about 16 million at its center. And so the slightly deeper portion of the wave will be traveling a little bit faster because its sound speed will be greater. The speed of sound goes like the square root of temperature. And so naturally, they will be shifted around. Some may noodle just below the surface, others go deeper down. These are ray diagrams. They don't really show quite the structure of the mode. But basically, the sun is a great organ pipe, but with unusual properties. It varies with depth, and these build your resonant modes. The other ones don't survive as well. They kind of interfere with each other, but there are certain humming tones that we drive, and some of these waves can last for months. So if we do a bunch of mathematics and say, well, so what do these waves look like? They correspond to waves with, if this is the surface of the sun, we ask, well, where is the wave? Well, the simplest so-called fundamental mode has a lot of power just below the surface. There's a P1 mode, pressure 1 mode, that has a node an overtone in the radial direction. There's another one that has 2. There's some that have 16, 18, 20. And similarly, the waves may occur are localized in different portions of the star. Some cover a lot of territory, others are more localized. So the issue is, how do you use information from these very different types of things to sample properties like temperature or the flows that occur at a given location. And that's inversion. Now, let me just go back and say, well, how many of these ridges can we, each of these ridges corresponds to one of these modes. This is the fundamental. No nodes on the inside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. It's a little bit like a fisherman, you know, how big is a fish? How many ridges do you have? But a very large number. And that's where these are the working tools. We can use these different modes. If where the mode is traveling, the sun is moving, it'll also shift its frequencies. A little bit like the Doppler radar signal that is being used. And so with Michael's work and the entire sort of community that's partly here, we've looked at the issue of, well, how well do we know the inside of the sun? And from stellar structure models and evolution models, we had some opinions that we were more or less saying that we know that the temperature of the sun at the surface is about 6,000 just by measuring it. And then there's the question of, well, what is the central temperature of the sun? And we think it's, from this various work in fitting the frequencies, we think it's about 15 million Kelvin. And does that matter? Well, it matters in the sense that there was a great puzzle with solar neutrinos, because we were seeing about 1/3 the ability to measure neutrinos, which is very difficult, compared to what we thought were sort of the best models that existed, that we thought the sun should be putting out much more neutrinos, so-called electron neutrinos, than were being observed. About 1/3 of the neutrino count that the theory said was being observed. And so the word was out, you people in solar physics don't know what the inside of a star is, you're off. You've got to reduce your central temperature. And if we did, we came into disagreement in a serious way with what the helioseismology was telling us. So what we call data is really the interpretation from the helioseismic measurements compared to what we think was the best model. And they were basically bang on. I mean, within a whole bunch of, we learned a lot about the internal physics of the star, the so-called equation of state and the properties of the plasma, but we were bang on. And finally, by building new classes of detectors for neutrinos, one found a very significant result, that the helioseismologists were not wrong, but the physicists were wrong in the sense that most thought the neutrinos had no mass, zero mass, and therefore, if you made an electron neutrino, it would always be an electron neutrino. The nuclear burning that goes on, so-called proton-proton chain, makes lots of electron neutrinos, but when they start flying, they're made and they kind of zip out through the sun. They don't get stopped by anybody. They don't collide with anything. So very hard to catch. But during the course of their flight, they get turned into tau and nu neutrinos, the so-called neutrino oscillations, not our kind of oscillations, but they get transformed. So although you made a certain amount, only 1/3 of the electron neutrinos will survive after 8 minutes of flight. And to accomplish that, neutrinos had to have a little bit of mass. Wow. And so Nobel Prizes were given, not for our work in helioseismology, but for the discovery that neutrinos change as they fly. So that was a significant issue, but also many other things. We could tell how deep was the convection zone. Again, that occupies about 30%, and many things about density, and basically very fundamental physics. Now, the other thing maybe we might say is significant, we could also see how the sun was rotating on the inside. And that ultimately left the special issue of Science magazine in 1996. Michael in all had about 270 publications, but a very significant one was where he led the team report on, from Gong data, what does the rotation of the sun look like? And then we've worked on this with the follow-on satellite instruments and so on. And the great surprise really was that although we knew from, if this is a cross-section cut of the sun, here's the surface, the equatorial region, here is the pole, and these colors represent what the sun is doing. We've known for a long time that the equator goes around pretty fast in about 25 days, and that the poles are much more leisurely, with almost a 20% contrast in rotation rate. That just below the surface, if we ask this angular velocities, how rapidly something is rotating, and we find that in fact it speeds up a short distance down, and then it's roughly constant throughout the bulk of the convection zone. And then at the bottom, where we go into the radiative interior, it all kind of goes bland. So it looks like the interior is rotating as a solid body. A major result, not anticipated. How is it that it was thought that maybe the interior could be rotating very much faster than the surface because the sun has been spinning down, slowing down, but instead the interior seems to be rotating at about the rate of the middle latitudes. And so this has come to be called a tachocline. Cline is a layer of change, like a thermocline in the oceans. Tacho looks like a tachometer on how rapidly your engine is rotating. And there's a near surface shear layer. And if we look at this by looking at some cuts with depth at the equator, 15 degrees, 30 degrees, as we go up, we can quite strongly see there's a near surface shear layer. And then there's all these branches come together in this tachocline. This transition could be much narrower. This is controlled by how much resolution we have in the modes that we have available. It could be extremely sharp, but that was a great surprise. And then another path that has been followed with helioseismology is not only to use the global modes, but to analyze the wave field in small patches. Michael was very much involved with that. This particular thing is called ring diagram analysis. What can we do with that? Well, we can look at different small portions of the sun and ask what the flows are. For instance, just below the surface, here's a big active complex, or deeper down in the convection zone, and we're seeing big streaming motions that are coming in. Great surprise that we'd expect that this turbulent convection has also large-scale motions, and it certainly is the case. And in fact, we can say that a little bit like meteorologists with satellites for the first time saw the great jet streams and other things on our planet, we can map some of these large-scale flows below the surface. Here are regions of magnetism, but you see these streaming motions. These are beyond what the differential rotation is, but this is at a depth of 7,000 kilometers. A familiar number to us, basically the Earth's measure. And we can do this deeper too. Now we have a number of different techniques that are used for this, but we're able to use this, and we might say, well, here's the flow field just slightly below the surface. So it has provided us with ways of imaging stuff inside the sun, but maybe the biggest are that we have constraints on what goes on with differential rotation. And so there have been many efforts in the last 10, 15 years to build whole global models of what happens in the convection zone. They use very big supercomputers, gobs of time, and they may even tell us something that's useful. And one of these is a Boulder product. But what we see is that the types of convection that occurs fairly self-consistently can establish we're in a rotating frame at the average rotation rate of the sun, and you see things are sweeping from the left to the right, and these are very large convection structures that itself are continuously setting up the differential rotation that we see. There's some technical details about how we carry these calculations out, but we largely know how the sun rotates. But why do we care about that? Because this, we think, is intimately related to how the sun builds its magnetic fields. And you can do similar things this is called a Mulwady view, where you're seeing the entire spherical surface at some depth, and how the sun is building and rebuilding its magnetic fields by dynamo action. But it depends crucially on the differential rotation that places constraints on it. And we're getting to the point where we understand how a large convection zone can build large-scale so-called wreaths of magnetism. So it's tied in very much to having observational evidence for how does the sun rotate, what constraints does it put on it, how does it depend upon things. We still have lots of ignorance with it, but we've come to the point where we can at least self-consistently build quite a few things about the differential rotation, and in some ways build the dynamo of the sun. And if we said, let's end with the final thing, if we cut in and said, well, what does a magnetic field look like on the inside? We've cut a bit of the stuff away. Magnetic fields going to the right are red, to the opposite sense blue. We think that from these wreaths that are there, sunspots probably come up. It looks nervous because the sun is nervous if we go into the inside. But there's a close tie-ins to with a number of folks, including here in Boulder, on using both helioseismology to put constraints on things, but also to try to build modeling of what may be going on constrained by helioseismology. And so let me end with Michael and Kate in one of the other conferences in December in Mumbai. And clearly they demonstrate they are Englishmen, English folks, because it's a beer of Stein. And we celebrate the things that Michael has done. I mean, we all would like to have eternal life. That doesn't seem to be quite our choice. But we've made some headway. He has made a lot of headway in a very collegial and lovely fashion, and we celebrate his life. So thank you very much. Of course. Would you like this mic or? Pardon me?
It's up there, okay. I don't.
Okay. Okay, is that better? Mic is now on. Right. I am honored to be asked to give this. As Yuri said, it's an impossible task, right? There are an awful lot of stars out there. And therefore, all I can really do is start from the sun, because that's where I started, and tell you a bit about some of the types of stars that are out there, and in particular, some of the types of stars that are quite like what our sun will become after this. I should also say that in terms of academic age, I'm roughly the same as Michael. The year he started his PhD was the year I got my faculty post, in local jargon, in the University of Birmingham. I was going to say I've never done any solar work. That's not true. I only ever did a PhD because I was shown a map of the Sahara and told there was an eclipse of the sun. If I wanted to do a PhD actually in some instrument building, I could, as a byproduct, come to the Central Sahara to see the longest eclipse that actually is possible. So I thought, well, okay, I'm not going to go and work in industry. I'll come and do a PhD. So I started in this roughly at the same time as Michael did. Our tracks were somewhat different because he was a brilliant mathematician, a theorist, and I was someone who actually built instruments. But obviously, the two are really quite closely connected. So we've seen this picture of what the sun is like inside, and we've seen that helioseismology is partly what actually lets us know what's there. Oops, sorry, I'm trying to find the right buttons here. So how do we know in detail the conditions that are inside? We know it from oscillations. As Yuri said, light doesn't penetrate through the photosphere, and actually, if the sun decided to be obtuse and just switch off its nuclear power, we wouldn't know about it. It would take a very long time for it to work its way, the effect, to the surface. But I can tell you from the data that we collect, because it takes only a few hours really for the sound waves to propagate. So I could say, guys, you might have to worry here. Michael's work was very important because I can collect you great data, but unless you can do something with that data, you're nowhere. And the remit I'm given today is to try and take you from the work that was done on the sun through to the study of oscillations of stars, which is given the smart name of astroseismology. And there is another Latin-Greek discussion to be had, which I won't have, but you can talk to Jan and Yuri afterwards. I will also say a little bit about activity. In other words, what Yuri was showing you in that we have an active sun, and ask the question, is that normal? And if it is normal, has it got consequences? So the very basic idea that we have here is that all stars that oscillate, so the sun just gently pulses in and out with a pulsation period, which was described in the 1880s. So it's a very well-known phenomenon, and we can estimate the period from the time it takes the sound to travel across the star. So for the sun, that's about an hour, hence why I could tell you within an hour what was going wrong. If you're looking at a star that's very much bigger, then clearly it takes a lot longer. You'll see actually that this is the fundamental, and as you might have picked up from some of Yuri's plots, we don't actually always see, the fundamental isn't always the strongest mode. Michael was very well aware that you can take what he and his collaborators were doing for the sun and take it through to other stars. So there was a conference that he organized with a couple of other people who are actually here at this meeting to look at what astroseismology was going to be able to tell us over a range of stars. The range of stars being described by the so-called HR diagram. Hertzsprung-Russell, Jan can correct my pronunciation, I'm sure, an American and a Dane, who came across the same idea of this way of presenting the data. And you'll see this graph a couple of times through. And in the sort of introduction to this, he was making it clear that we stand at the threshold of an exciting time, absolutely true. But the aim of the organizers was to actually make people talk to each other. And you've heard many discussions through today, and we'll hear it over the next couple of days, as how Michael was really good at making people talk to each other. He also reckoned that it wasn't going to be easy. And unlike some theorists, he recognized the observations weren't necessarily trivial, but observation, data analysis, and theory all pose hard problems. So this was in 2002, before we got the really great data, but on the start of an era when we expected to begin to get the data. You've seen these two different sorts of oscillations. So the one, I'm very bad at left and right. The one on this side is the P, and then when I have to reverse it to talk to an audience, I've had it. The P modes tend to show you the outer layers and to an extent in towards the core, but as Yuri said, the sound travel time is such that they'll tell you more about the outer regions because they spend more time there. Alternatively, we can have these so-called G modes, which are very concentrated in the core. But if you think about a parcel of gas, it can either sit and oscillate, That's a G mode, or at least it won't quite like that, but it'll sit and oscillate with buoyancy, pulling it back. Or it can have large-scale convection, in which case it goes to large distances. But it can't do both. So these G modes that want to oscillate just like this don't like the convection zone. So they're strongly attenuated by it. And as been indicated, it's one of our goals for the sun to try and measure them, but I will show you that for other stars, actually we can get them quite straightforwardly. There are different mechanisms for getting the oscillations, a so-called kappa mechanism, which I won't discuss, but the one that is common to the stars I will discuss is the convection that you've very nicely seen. And as I said, you don't always see the fundamental mode. So the huge, huge expansion of data came with 3 satellite missions: CORO, French-led, Kepler, NASA, and TESS, NASA also, we get that right, which came in sequence, and TESS is still actually up there working. CORO was very groundbreaking, and Kepler has just given us unbelievably wonderful data. I will mostly talk about individual stars, but it would be remiss of me not to point out that we exist in a universe, and one thing we'd really like to know is how we fit into the Milky Way. I came to Boulder thinking I'd get good skies and I could actually see the Milky Way, unlike I get from light polluted England. Sadly not, but the Milky Way is the plane of our galaxy, and Kepler can look out of that plane and will tell you something about the evolution of our Milky Way. So it's an interesting actual change right now. If you were a cosmologist, stars were very boring. These days, most cosmologists are now beginning to realize that because we can tell you so much about stars, that actually they can be a good deal more accurate, precise, predictive about their models. So actually, it's a real renaissance in an understanding of stellar structure and evolution, partly driven by this so-called galactic archaeology. We're back to our equivalent of an HR diagram, oscillators all over the place. I think Jan drew the first one. I've marked up here where I've taken people's pictures, and that's the source, but Jan was the originator. And what I'm going to concentrate on is the one shown by the little ellipse, the black ringed ellipse, which are the solar type oscillators. These are the ones driven by convection. There are many others. You could give thousands of different talks around this. So I had as a title, How Stars Work. Okay, so one of the interesting things is, well, what are the different zones inside the star? Well, we've seen that there's the photosphere, there's a convection zone, there's a radiative zone, and there's the nuclear core in the middle. We might want to ask where the boundaries are. That's clearly very important. Have we got a tiny little convection zone or a big one? How much nuclear generation is going on and where is it going on? And one has to say that it's dead easy, well, inverted commas, dead easy to build a model if you have one system. If you have to make it work over thousands, where the conditions are slightly different, good deal more tricky. I can remember 10, 15 years ago when I was going around looking at people's research grants and assessing them, and the research councils were saying, solar system studies, we're not going to fund that. We understand how our solar system works. And then you go and find some extrasolar planets and you just discover, oh, no, you don't. Oh, no, you don't. So that's one of the great challenges, is to try and broaden the scope and make things work over a wide parameter space. You've seen the picture for rotation. I could have put a big question mark in the center of this. You can get down, if you really push it, to about 0.2 of the solar radius. What's going on in the center? Very tricky. We don't really know. It's controversial, which is fun. For the sun, it's really difficult to get a measurement of the core because of the difficulty in seeing the so-called G modes. That's not true for evolved solar type stars, where you get a mixture of the P mode links to the G mode and then extracts that information towards the surface. However, there's a penalty. You can't make the kind of detailed maps. So the kind of modes that Yuri was showing you in the outer layers requires you to be able to image really, 4K by 4K. Sadly, we can't do that for lots of stars. We can do it for the sun. You might get a few pixels across a really big giant, but basically you're stuck with the modes that are the whole star, the whole sun, which is the ones actually that for the sun I specialized in, so I'm quite happy. But it does mean you can't produce the kind of detailed imaging. You have to have a slightly different approach to things. We expect to find cores that rotate faster than in the sun. We have the problem with the sun, right? That we might have expected it to be going around quite fast. Doesn't appear to be so. But for stars, as they evolve and get older, we do expect that there is more differentiation between the speed at which the surface travels and the speed at which the center travels. I throw this in, and I'll pass fairly rapidly over it, but there is some evidence that the tachocline isn't actually always there, and yet you have magnetic activity. I'm hoping someone might address this over the conferences. I did see if anyone had rejected this, but the modern papers don't seem to have done it yet. Okay, so our sun sits here and burns hydrogen into helium in a slow, sedate manner. All things come to an end, and eventually it's going to burn up the hydrogen that it's got, and it's going to have to start changing the way things are. And when it does that, it actually changes much more rapidly, but it also becomes bigger and denser in the core, so it gets more differentiated. And then you get to something that's called a subgiant. So, as I said, there are problems that you can't build the beautiful maps that you can do for the sun, and you have an expectation that because the center is collapsing, then conservation of angular momentum, the classic ice skater pulling in, it's supposed to spin nice and fast. So there was some very nice work done by Sebastian de Hervels using Michael's methods. And he discovered that he could measure, if you look at the lower graph, that the outside for these different stars were going quite nice and slowly, and that the inside was going quite nice and fast. And as you change the temperature of the star, in other words, you looked at different stages of evolution, then there was a sequence, there was an evolution. But the center was not going round anything like as fast as people thought it was going to go. So we still have an angular momentum problem. And I'll come back to red giants in a few minutes, but for them, which is an even later stage, so they're huge stars, it's taking a very long time for the sound waves to go across them, but they have beautiful mixed modes, so you can measure the rotation rate, and observations do support a nice fast core, but again, much more slowly than theory predicts. And there's an even later stage where actually it's a bit slower. So lots and lots of problems to solve. And actually, I'll go back one. Lots and lots of problems to solve there. Okay, right, slightly different topic. There is helium formed at the very beginning of the universe. It's one of the few elements that's actually made. And therefore, we think that our sun started off with some hydrogen, with some helium, and some heavy elements, okay, which are the result of other stars having evolved. We'd like to measure the amount of helium, but the normal methods really don't work. But there is a method that does work, and that is essentially to look at the thermodynamics. There's a quantity called gamma 1, the first adiabatic exponent, and that puts a little glitch into a pattern as you go into the sun. And that little glitch alters the frequencies. And Michael did a lot of work on this to show that actually there is a signal in the oscillation spectrum that will tell you about this ionization zone of helium and the location of it and the amount of helium there. So that is a really crucial measurement. So he did work on the sun, and it has been applied to a whole load of Kepler stars, but in this case to give you the depth of the convection zone. So the ideas that he developed were transferred across, in discussion with him, into a slightly different field, which now gives us quite a decent idea as to where some boundaries occur inside much more distant stars. Yuri's told us that Michael did a lot of inversions. He developed a lot of the theory. There are real problems doing the inversions on distant stars because we lack the high degree modes. So we have the different modes probing the different region, but we're very limited in the modes that we have, only the low degree modes. So basically we can say things about the core, but we can't say so much about the envelopes of them. So the methods that Michael developed were modified for the sun, and many people work on it. There will be several talks here tomorrow about it. I have a phrase that the BBC often use when they're not allowed to advertise. Okay, at least they can advertise in America, but if I listen in the UK, they can't advertise. So if they inadvertently mention someone's name and a product, they say, other products are available. Right. So there are several products available, and I will not mention them. But the general idea is that instead of stopping when you have a solution, you think, is that the best solution I can produce? So you go away and explore a whole load of different ones. So you don't stop, but you need methods that are efficient for doing it. And the philosophy of so-called machine learning, you don't just sit there and look at them yourself. You get a machine to look at all these things. Sometimes machines don't get the right answer, but it's a really booming field as we try and cope with this vast number of stars we have and want to try and make the models work over this wide range. So the kind of phrases you'll hear are the undershoot, the overshoot. Particularly interesting thing for astronomers is that you have this nuclear core, and for the sun, we think it's quite stable. But when the stars get a bit more massive, convection starts to kick in actually in the cores, and that changes evolution quite significantly. So we'd like the boundary for where that happens in mass, in composition, rotation, all sorts of other goodies. So we want to be able to do this in many stars, automated, reproducible, and efficient. That's one hell of a challenge, actually. This challenges and improves theory, and one of the great joys, actually, of this field over all the years I've been in it is that theorists, observers, and data analysis people talk to each other, and one drives the other. It's not two, three, four separate communities. And Michael, as I said, was very good at trying to pull all these together. Right, modeling of Kepler stars. I'm just going to give you a couple of numbers. You have to remember that Kepler's main focus was planet finding. And astroseismology, courtesy of Jan, I guess Michael also had a hand in it, convinced NASA that we were the best thing since sliced bread. That if they'd but let us have the data for free, we'd promised to close our eyes to any planets we found, but we could tell them things that they needed to know. And as an example here, this is a particular Kepler system fairly early on, but all I really want you to look at is the precision. So we're talking about a star 1.34 plus or minus 0.06, and the radius is 1.86 plus or minus 0.4. Right, if you were to measure your height, how accurately do you think you would straightforwardly measure your height? Would you stand up straight? Would you flatten your hair? Right, and this is a distant star and planet, and we're getting these fabulous precisions of it. And this is a mixture of clearly the planet finding stuff, the transits, but also what astroseismology can actually give to you. I found this on Kepler, on the mission. Lots of goodies, years in space, number of stars observed, and so on. The thing that absolutely astounded me, and I'll lose the mic for a minute, is that one down the bottom. It used 3.12 gallons of fuel in 9.6 years in space. And American gallons, I guess, at that. Can we try and get that kind of efficiency? And, anyway, I thought that was absolutely stunning. And to me, totally, I had no idea when I looked at it. Okay, so red giants, something that I've started to work on and one of my pet projects. Totally unexpected success. They were added because they are seen to big distances and because they're big and therefore they're bright. And therefore they provide a sort of universal frame in which you can actually judge where you are. So astrometric. And some were there by mistake because they tried to pick out all the main sequence stars, because what they really want is planets around main sequence stars. The stars are big, so the oscillation periods are long, and that's an absolute pain from the ground. Just think about it. You get 6 hours perhaps observing it a night, and the periodicity of this star is 6 hours. You're in some trouble. Then you've got to go away because the sun rises. I'm interested in that, but not if you're interested in stars. But if you're working from space and looking in the same direction all the time, where's the problem? And what's more, because these are long times, you don't have to measure it very often to get lots of measurements through a period. So 30-minute cadence, 30-minute periodicity was fine. That's not a burden to telemetry. So we got lots and lots and lots of them, 100,000 perhaps. And there were some very exciting results early on, real groundbreaking ones, and there's still a huge amount of work going on. But I want to just tell you a bit of the groundbreaking ones. So I have here an HR diagram again. It's a picture from one of my colleague, Andrea Miglio, and the dots are Kepler stars of different masses. And on there are some tracks of stellar evolution, which sadly don't match the color scale, but ignore that. Okay, so we're quite interested in the point where you don't just burn hydrogen, but you start to burn helium, the next element up. That changes the landscape considerably. In terms of the HR diagram, it's about there. And you can see from the different tracks that if I change my parameters just a little, all these overlap. So it's an absolute pig to try and work out whether or not helium burning has started. So very difficult from the surface, but you can do it from the ground. Now I have some modern pictures just taken from stuff I've done, which is mixed modes, and I'd like to look at them and just try and think how you would describe them. So this here is one particular sort. So the vertical lines are the radial modes, so it gives you some idea. And then there is clearly structure, but there's a lot of empty space in between. If I go here, it's littered with stuff, right? And that's quite characteristic. But this isn't as random as it looks. I can actually measure the spacing in these ones. And in some cases, I can measure the spacing in there, but the reason I can't do it is it's very small, so they're within the line width, really. That is a huge distinguishing feature. Let's move on one, which I didn't ask it to. So-called period spacing. So what we find is we can put the stars into different regimes. These ones up here have the quite large period spacing. They're the ones where helium burning has started. This sequence down here are the ones where we're still burning just hydrogen and not helium. And they, because of the difference in the core and the difference in the physics, the kind of physics that I was brought up to see in low temperature laboratories actually, matter that's very degenerate. In the laboratory, that's a small fraction of a degree Kelvin, perhaps 4 degrees Kelvin, perhaps. In stars, it's 1 million degrees. Conditions are slightly different, but nevertheless. So that was a fantastic breakthrough from Kepler. We could also measure the rotation in the same way I described for you for the sub-dwarfs. Right, again, different solar activity. You've seen these pictures. There's a solar activity cycle. The sun has an 11-year cycle. I'm going to show you some data from Birmingham where we measure the frequencies of the oscillations, and we discover that the frequencies change with activity. So I have a plot here that has a vertical axis that tells you how much my frequencies have changed, and a horizontal axis that is time over 3 solar cycles. And on top of that are plotted various different index measurements that you might choose, like the sunspot number, and there are various other things. And the correlation looks quite reasonable. Now, in the nature of these things, the early data we had weren't as beautiful as this. I sometimes show it to PhD students to make the point, if it looks like this, there isn't a paper in it. You've done it. But the question arose, is this cause and effect, or is it pure chance? And I want to show you an item from nature that you may decide is cause and effect, or you may decide is pure chance. 1988, so very much similar time, the role of storks in live births. And there's an absolutely straight, serious paper, a very short letter to Nature, which shows you 2 graphs. On one axis is the number of live births as a function of time, and the other axis is the number of breeding pairs of storks as a function of time. You might decide that that is not cause and effect. In terms of the sun, Michael was able to show that there was a process whereby you could have cause and effect, and therefore we could believe that magnetism was actually very important from this, and that magnetism was located very close to the surface. So stellar activity is clearly the next step you would go to. There's lots of recent data. We're discussing some of it today. We'll discuss it on. There's an interesting concept that the sun occasionally goes really quiet, so-called Maunder minimum, and we lose the sunspots. And then you get into, is this cause and effect, or is this random? But there are climate associations with it, particularly actually in Northern Europe. You need long-term observations, and that's quite another topic. But the thing I wanted to raise here was, is this relevant for life? If you try and think how life actually might have formed on the Earth, and you see discussions trying to produce, Robin can put me straight here probably, trying to form the sort of complex molecules that one needs, does ionizing radiation play a role? Does it kill off anything that happened to form? You don't know. But when we're looking at planetary systems, actually it's a question that people ask. What is the role of activity? Is it important, or is it actually a problem? I'm not going to take that further, but it is an interesting question. Often this subject is called the songs of the stars. So there's the song of a star. Actually, he's only playing the notes, but I have heard him sing. I've heard him sing on the telly in some of these carol concerts. So I'd like to finish by saying that Michael really did lead the way in providing us with a wonderful solar-stellar connection. Thank you.
I don't know. I'm trying to ask myself that. It's not on. Yeah, I'm gonna fold it in. Yep, there it is. Good.